All right, this time we're going to do a problem about a bracket. And this is, as you can see from the diagram, a 3D problem. So I go swim at the Ark 2 or 3 times a week, and they have these brackets here that I put my laptop that has all my lecture notes and everything inside of it and all my research documents. Of course, it's all backed up on the cloud, but still, I do trust that these brackets are pretty well made. And so here, I've drawn a diagram of what one of those brackets are, a simplified one, and I've taken off that front bit to show that what if I put my bag on there a little bit wonky so that it was only acting right with a force at that one edge, specifically this edge right here, drawing on the PowerPoint slide. And so what I'm asking is, given this incredibly heavy bag and the angles shown, and note here that the z component of F1 is in the negative, find F2, the resultant force. What I want is the resultant force to be in the xy plane. So I don't want any forces coming out that might pull this thing out of the wall, and the magnitude of the resultant force. Okay. So this is basically a 3D particle type resultant force problem. And it's sort of a discrete version of the equations of equilibrium, right? Because I want the resultant force to act only in the xy plane, which means what? For the resultant force to be in the xy plane means that the z component must be equal to 0. So now we know the two forces acting are F1 and F2, so let's figure out what that z component is, set it to 0, and that's solve, right? For whatever this F2 is that needs to offset the F1 z component. Okay, so we'll take a look first at what's going on with this resultant force F1. So I'll just draw F1 here. Not really a free body diagram, but just trying to zoom in so you can see. So notice that z, x, y, so I could have drawn that a bit more vertical. And just notice that F1, right, is pointing in the negative x direction, in the positive y direction, and in the negative z direction, right? So its shadow sort of is back here, right, on the ground. All right, so I think the hard part is just visualizing what's happening in terms of these angles. So we're given the angle between F1 and the x-axis here. Let me erase these shadows. 50 degrees. The angle between F1 and the y is 60, right? And then we don't exactly know what FZ is, but we do know it's basically pointing negative based on the way the diagram is drawn and the fact that I've given you that information here. Okay, so let's find the components of this force vector F1. So F1x is equal to F1, right, cosine alpha. So this is using the law of cosines that were in one of the early lectures, right? So that's going to be equal to 60 newtons. And then what is the alpha though? We want it with respect to the positive x-axis. That's the trick with these cosine laws, is that this must be with respect to the positive x-axis. So if you put in 50 here, we'd be in trouble. So we really need it as a function of this here. And this, of course, is 180 minus 50. So this is now cosine of 130. The F1y is a little bit more straightforward. So this one's going to be the 60 again. So I'll write out the equation for you. F1 cosine, I guess we can call that beta 1. And beta 1 equals 60, right? 60 newtons cosine 60. That's going to get you some answer. And now F1Z, the Z component, is F1, which we know, but it's cosine, whatever the gamma one is. And that's the one that we don't know with respect to the Z, right? But we know the resultant force, right? We know that F1 x squared plus F1 y squared. Pretty messy today. F1y squared plus F1z squared must be equal to 60 newtons squared. So when you plug that all in, what you should get, so it's a good time to pause and see if you're on the right track. Now that you're back, check. Did you get that F1z is equal to 34.82 newtons? Now again, we know that this is pointing in the negative direction, so this needs to have a negative sign in front of it. So F1, therefore, is equal to negative, see if you got all your answers right, 38.57 I hat plus 30 J hat minus 34.82 K hat, and that gives us F1. So now our unknown is F2. And we can see F2 has 0 component in the I hat direction, 0 component in the J hat direction, and then some unknown F2Z in the K hat direction, right? And the whole point of this problem is if the resultant force is supposed to lie in the XY plane, then these two need to balance each other. So by inspection, you can see that F2Z must equal a positive 34.82 newtons. So there's F2. And now what is the resultant magnitude? So R is basically just the X and Y can be 8.57 I hat plus 30 J hat squared, squared, square root. So we really just need these magnitudes. And you should come up with that R is equal to 48.9 newtons. There you go.